Okay, this example is called the maximum flow. Um, we want to find out if how much is the maximum flow we can have between two specific nodes in a graph. For example, if the amount of product or power or whatever is entering the node 0, um, and we are expecting that there is no losses is happening in the system. I repeat, it's not an electrical engineering kind of system, but it's a general form. And we want to know if we enter G to the node 0, is it possible to take out G from node 6 or any other nodes without violating the capacity of these lines or these routes? Okay, so in order to do so, we have to write down the balance equation for every node. So as you can see, only one node has generation, which is node 0, for example, in this example, and the rest of them they have no generation, but and no demand, and also only one node has demand, which is node 6. Okay, so and it's equal to G. So we want to know how can we formulate it as a optimization problem in Pyomo. Okay, so here you can see that we import the required packages, and then I create the model, abstract model. So this is the set. It is initialized with the range between 0 and 7. So it will be created 0, 1, 2, 3, 4, 5, and 6. J is the alias of that. Flow is telling us how much flow is happening between I and J. It's a positive number. And also the capacity of each route is also specified by parameter cap. G is a variable telling us how much we can inject to one node and extract from the other node. An objective function is defined as G. Okay, so here let me continue. So I have to write down the balancing equation for every node. So the first node, which has generation, is written this way. So if I is 0, this is this way, and if it's the receiving point, this is written this way. But if it's none of any of those two types, then there is no generation, no load, and that's the constraint defined for every node. And also the flow should be always less than the capacity, and the constraint is defined over I and J. The rule is C2. And the objective function is expression model G. So this way you can see that I don't need to define an extra variable called OF. Okay, it doesn't give me anything else, so I can remove it for simplicity, and I choose the solver as the GLPK. So the unknown parameter I haven't discussed it so far is the capacity. So the capacity should be specified in the DAT file. So you can see it here. It's a kind of table specifying how much is the capacity between each pair of nodes. And you can see that in this specific example, it's not symmetrical. So the capacity between 2 and 1 is 10, but between 1 and 2 is 0. So it's a directed kind of graph. Okay. You can change the numbers if you want and see the impact. So it will read that data file and put it into the Pyomo and ask it to solve it. Okay. So you can see here that I can plot the results and show you what's happening. So I run it and I explain what's happening at each stage. Okay, so the model is solved here and the data is given here. So I want to plot that graph, so I put a circle and connect the connected points, and the capacities are somehow graphically shown here. The routes with higher capacity are specified with thicker kind of lines, and also you can see the objective function is 7. Okay, so this is the maximum amount of energy that is capable of passing from 0 to 6. And there are some useful information regarding the solved example. So just have a look at the this instance.display. We want to find out if our modeling approach is efficient or not. Okay, so so how much is the maximum capacity? It's it was 10 in the data file. Okay, so we could also specify before I explain that, I just have a look at the variables. The variable is flow G, and what else? Objective function is something else. Okay, so there are two main variables, G and flow. So just have a look at the status of each variable. Okay, so as you can see here that we have a variable called 0 and 0. It means that the flow between node 0 and node 0, which is not going to be true because I don't need that kind of variable in my model. Okay, so why is it created? Let's have a look at the model, the way I wrote it. So here you can see that I have a condition that I should be different with J, the same here. So this constraint is not creating the problem for me. This is the one. Okay, so because I am defining it for every pair of I and J. For small problems, it doesn't create that much hassle, but for larger kind of programming, it should be definitely avoided. So let's put a condition here. Let's say if I is not equal to J, then return this, else return constraint dot skip. Okay, so if I run the code again, I hope I avoid that. What happened? Okay, so the problem is solved, but here let me check. So there is no combination of 0 and 0 and 1 and 1 and so on and so on. Okay, so in order to check what is happening here, I have to see this line. Okay, so let's have a look. So it is telling me that it is trying to access one specific component of a flow which doesn't exist. It can be understandable because now let me do this in this way. Okay, so I put it here. If value is bigger than this, then plot it. Okay, I hope this time it resolved the problem. Yeah, very good. And run the last tab and see the results. So you can see here that yeah, it doesn't exist in the model. The stall is now true. It means that it doesn't it's not included in the model. Okay, and it doesn't have any value, as you can see here. And also there is another point that can be considered, and it's the fact that there is no upper bound for the flow. Okay, so it's none. So it's always, as I said before, it's always good to have a bound for your variables. So I even if it's not very tight, but at least it's something right there. So if I run the code again and let's run all the tabs and see the results. Okay, so as you can see here, the upper bound of the variable flow is now determined. Okay, so these are the steps that you can follow to improve the way you